In the vast silence between galaxies, a faint whisper lingers. A breath of light so old it predates the stars themselves. It fills every corner of space, not as a blaze, but as a quiet sea of invisible fire. Once it burned with the fury of creation. Now, it drifts through eternity as a pale afterglow, a ghostly residue of the universe's first awakening. This is not the light of suns, nor the shimmer of distant galaxies. It is the memory of birth itself, stretched and thinned by billions of years of cosmic expansion. Each photon, once brilliant beyond imagining, has been slowed, cooled, and softened into the faint microwave hum that blankets the sky. It arrives from every direction, unchanged since it began its journey nearly 14 billion years ago, when matter first learned to exist apart from light. In the quiet hum of an old radio, in the flicker of static on an untuned television, traces of this light still breathe. It is the universe speaking in frequencies too ancient for language, a relic of an age when time was young and silence was still learning its shape. Astronomers call it the cosmic microwave background, the afterglow of the Big Bang. Yet, it is more than a signal. It is a memory so complete that it remembers everything that has ever been, a fossil made of light, carrying within it the story of the universe's first breath, and perhaps its last. And so the question lingers, fragile yet immense. What is this ghost light that never died? What secrets of creation still burn inside its endless whisper? If light remembers, then the universe is not silent. It is haunted by its own beginning. In the early 1960s, at the edge of a quiet New Jersey field, a strange instrument pointed toward the heavens. It was not built to seek the dawn of time, nor to listen to the ancient whispers of the cosmos. It was born from the age of radio and secrecy, a relic of the Cold War, where sound and signal had become weapons of information. This machine, the Holmdel antenna, stood like a vast metallic ear, a smooth flared horn of aluminum and steel, its curved surface catching invisible waves that rippled through the sky. At its base worked two men, Arno Penzias and Robert Wilson, engineers at Bell Telephone Laboratories. Their mission was simple, at least in design, to test radio communications, to refine the art of signal clarity for the next age of technology. They were not cosmologists or philosophers. They were builders, troubleshooters, minds tuned to the world of electronics, not eternity. Yet through their work, the quiet field of Holmdel would soon become the place where the universe first revealed its own memory. The year was 1964. The air was heavy with the hum of human progress. Satellites circled Earth, radio waves stitched continents together, and telescopes reached deeper into the void than ever before. But in that field, a smaller hum persisted, one far less cooperative. Each day, Penzias and Wilson climbed the steps to their gleaming horn antenna, taking measurements, calibrating instruments, checking amplifiers and fine-tuning receivers. And each day, a faint, stubborn hiss greeted them, a steady background noise that refused to vanish. It was everywhere, constant, indifferent to the direction of the antenna. No matter where they aimed it, toward the Milky Way, away from it, across the horizon, the noise remained, an ever-present static, soft yet unyielding, like a whisper that refused to stop speaking. At first, they assumed the fault was local, a miscalibration, a defect in the equipment. They replaced cables, cleaned contacts, and adjusted the amplifiers that measured the signal. But the hiss persisted. Next came suspicion of the environment itself. Could the radio city of New York, glowing on the distant horizon, be polluting the signal? Was the Earth itself, or its atmosphere, humming faintly at their frequency? But no, the noise did not rise or fall with direction or time. It came from everywhere, and from nowhere in particular. Then came the pigeons. High in the flared mouth of the antenna, two white pigeons had built their home. They nested in the structure's curved walls, leaving behind what the engineers politely called a uniform white dielectric material. In truth, a coating of droppings spread across the metal interior. Perhaps they thought this was it, the source of the noise, a contaminant scattering the signal. So they captured the birds, cleaned the surface with care, and restored the antenna to its pristine state. But when the system powered up again, the hiss returned, unchanged and eternal. No matter what they did, the static remained. Across the continent, in Princeton, New Jersey, another story was quietly unfolding. A team of physicists led by Robert Dicke had been working for months on a very different problem, one that traced its roots back to the earliest days of cosmological theory. Ever since Edwin Hubble had revealed that galaxies were rushing away from one another, the concept of an expanding universe had taken hold. But if the cosmos was expanding, what had it been expanding from? Decades earlier, physicists like George Gamow, Ralph Alpher, and Robert Herman had predicted something extraordinary. If the universe had once been filled with a hot, dense plasma, an ocean of energy and particles so thick that light itself could not escape, then when it cooled, the leftover radiation should still exist. It would no longer be a blinding inferno, but a faint, cooled afterglow, stretched across the sky in every direction. The fossil light of creation. They had even estimated its temperature, just a few degrees above absolute zero, invisible to the eye but detectable by radio instruments. For years, the prediction had sat in the margins of theory, elegant but unproven. Few had looked for it, no one had found it. Until now. At Bell Labs, Penzias and Wilson had no idea that their persistent hiss might be the very echo those cosmologists were searching for. And in Princeton, Dicke and his team had no idea that two engineers, only 60 kilometers away, had already stumbled upon it. The connection came through a single phone call. A mutual colleague, Bernard Burke of MIT, learned of the strange noise at Holmdel and realized its potential significance. He arranged contact between the two groups, and when Dicke heard the description of the noise, isotropic, constant, matching the exact predicted temperature, he turned to his team and said quietly, "Well, boys, they've found it." In that moment, theory met observation, and the universe revealed its oldest secret. The static in the sky was not a flaw in machinery, nor the hum of the atmosphere, nor the echo of distant cities. It was the afterglow of the Big Bang, light that had traveled through nearly 14 billion years of cosmic time, cooled and stretched by expansion until it arrived as a faint microwave whisper. In the months that followed, the two groups published their findings side by side. One paper, from Penzias and Wilson, humbly described the detection of an unexplained isotropic noise. The other, from Dicke's team, provided the theoretical framework, the interpretation that this was the cosmic background radiation long predicted by Big Bang theory. Together, they completed a puzzle that had lain unsolved since the dawn of cosmology. The universe, it seemed, was not dark and silent after all. It was glowing, faintly, evenly, eternally, with the memory of its own creation. For the first time, humanity had touched something older than galaxies, older than light itself as we know it. That faint static was not merely electromagnetic interference. It was the echo of an age when the cosmos was young, when every atom now scattered across the stars was still part of a single luminous sea, when temperatures burned at thousands of degrees, and the first photons scattered endlessly through a fog of matter and energy. It was the last cry of a universe becoming transparent, the moment when light broke, free from matter, and began its long journey outward. And somehow, impossibly, those photons were still arriving, still speaking, still burning with the story of what they once were. As astronomers began to study this signal, they realized it was everywhere, perfectly uniform across the sky, to 1 part in 100,000. That symmetry spoke of a cosmos born in balance, expanding equally in all directions. Yet even in its uniformity, there were tiny imperfections, minute fluctuations in temperature that hinted at the seeds of all future structure. Galaxies, stars, planets, and life itself, all born from those first subtle ripples. But in 1964, none of that was yet known. All that existed was the hiss, the quiet, stubborn presence of something ancient, something vast. The engineers at Holmdel had stumbled upon the greatest fossil in existence, not of bone or stone, but of light. They had become the first to hear the universe remember itself. The Holmdel horn antenna would later be recognized as one of the most important instruments in human history. Its discovery reshaped cosmology, shifting the Big Bang from speculation to evidence. It forced the scientific world to reckon with a profound truth: that the universe had not always been, that it had a beginning, and that this beginning could still be heard. In the static of the sky, the universe had left behind its signature, not in words, not in images, but in temperature and frequency, a perfect blackbody spectrum at 2.7 kelvins, the afterglow of an event that marked the birth of everything. And though it was faint, quieter than a whisper, colder than deep space itself, it carried more information than any book, any archive, any fossil ever could. Every photon in that radiation had been traveling since the dawn of time, stretched by the universe's expansion into a faint microwave tone that fills all of existence. To detect it was to touch the first moment of light, to witness, not just with the eyes, but with instruments that listen to the very bones of reality. In the stillness of the Holmdel field, the antenna continued to hum, as though the sky itself were breathing. The sound was no longer noise, it was history. It was origin. That faint static, once thought to be error, had turned out to be the most profound signal ever heard. The whisper of the universe's own birth cry, echoing endlessly through the dark. And so, in the gentle hum of microwaves and metal, the first human contact with creation had been made, not by astronomers gazing through telescopes, but by two engineers cleaning the sky of unwanted noise, and finding instead the oldest signal in existence. The discovery spread quietly at first. A few papers in the Astrophysical Journal, a set of graphs showing temperature curves plotted in the simple ink of laboratory precision. But within months, those faint lines became the tremor that shook the foundations of cosmology itself. For decades, the idea of a universe with a beginning had been both fascinating and divisive. Some scientists clung to the steady-state model, a cosmos eternal, unchanging in its vastness, forever creating new matter to fill the void left by its own expansion. Others argued for the Big Bang, a theory first whispered in the 1930s by the Belgian priest and physicist Georges Lemaitre, who dared to suggest that all of space and time had once been contained within a primeval atom, a cosmic seed. To many, the notion sounded less like science and more like theology dressed in equations. An eternal universe felt safer, free from beginnings, free from endings. The Big Bang felt too abrupt, too violent, too absolute, but the faint hiss from the Holmdel horn changed everything. It was not the voice of the present cosmos. It was the afterglow of something older than any star, older than the galaxies themselves, a fossil made of light. When Arno Penzias and Robert Wilson described their discovery in 1965, cosmologists realized what it meant almost instantly. This radiation was everywhere, perfectly uniform, arriving from all directions, unbound by the rotation of the Earth or the shape of the Milky Way. It was not local interference. It was not atmospheric noise. It was the relic of an event so ancient that even time, as physics defines it, had only just begun to exist. The universe, once thought to be eternal, now had a measurable age, roughly 13.5 billion years, a number that would later be refined through decades of observation. This faint, cold light was the fingerprint of creation itself. To understand the shock of that revelation, one must imagine what the early universe was like. Not a space filled with stars, but a furnace of pure energy, a plasma of photons, electrons, and protons, entangled in a blinding, featureless fog. In those first hundreds of thousands of years, the universe was so hot and dense that light could not travel freely. Every photon scattered endlessly off-charge particles, unable to move more than a fraction of a millimeter before colliding again. The cosmos was opaque, glowing not with starlight, but with its own imprisoned radiation. Then, as expansion continued, temperatures fell. At around 3000 kelvins, something miraculous occurred. Electrons and protons combined to form neutral hydrogen atoms. For the first time, light could move without being scattered. It broke free from matter and began to travel outward, an exhalation of the universe's first breath. That moment, now known as recombination, marked the end of the cosmic dark age and the beginning of transparency. The light released then has never stopped traveling. Over billions of years, it has been stretched by the expansion of space itself, its wavelength elongated until it cooled to a mere 2.7 kelvins, just above absolute zero. What was once a blinding fire has become a faint microwave glow, invisible to human eyes, but filling every inch of the sky. This is the cosmic microwave background, the first light, the oldest memory, the echo of everything. For scientists of the 1960s, the implications were overwhelming. This was not merely another astronomical observation. It was evidence that the universe had once been in a state of unimaginable density and heat, that it had emerged from a singularity and expanded ever since. The Big Bang was no longer a speculative idea. It was a measurable event, written in radiation itself. The steady-state model could not explain it. No theory of eternal equilibrium could produce such uniform, isotropic light. Only a single explosive origin could. Physicists began to reconstruct the early timeline of the universe, tracing backward from that glow. They found that within seconds of the Big Bang, the first particles had formed. Within minutes, nuclei of hydrogen, helium, and lithium emerged, the primordial elements of all future matter. And after hundreds of thousands of years, the universe released its first light. That light, now cooled and faint, is what Penzias and Wilson had detected. The visible proof that everything had once been one. In laboratories and observatories, scientists began to listen anew to the sky. Every direction, every patch of darkness between stars sang the same tune. No region was brighter, no shadow deeper. The radiation was astonishingly uniform, a cosmic equilibrium that spoke of a smooth, balanced birth. Yet the perfection of that uniformity was also a puzzle. If everything began so evenly, how had galaxies, stars, and planets ever formed? Where were the seeds of structure? Those answers would come decades later, with satellites like COBE and WMAP, which would reveal subtle temperature variations, the ripples of density that would one day grow into galaxies. But in the 1960s, the shock was still fresh. It was as if humanity had, for the first time, stepped into the echo of its own origin. The discovery did more than confirm the Big Bang. It changed the philosophical shape of the cosmos. It meant that time itself had a boundary, that there was a before which physics could not yet reach. It meant that the universe was evolving, cooling, aging, not eternal, but transient, finite, alive. For some, the realization carried an almost spiritual gravity. To know that the night sky was glowing faintly with the residue of creation, that every point of light, every atom of air was once part of the same cosmic furnace, was to glimpse a unity that transcended everything else. For others, it was unsettling. If the universe had a beginning, might it also have an end? If creation had a spark, might it someday fade into silence? In the years that followed, the faint hiss from the sky became a language through which cosmologists learned to read the universe's past. The radiation spectrum matched a near-perfect black-body curve, an unmistakable signature of thermal equilibrium at a specific temperature. No known process other than a hot, early universe could have produced such purity. Its frequency distribution was identical in all directions, further confirming its cosmic origin. Every measurement, every test, pointed to the same conclusion. This was the remnant of the Big Bang. When NASA's Cosmic Background Explorer, launched in 1989, mapped the radiation across the entire sky, its data aligned almost perfectly with theory. The shape of its spectrum matched the predictions made decades earlier to a precision of 1 part in 100,000. The afterglow of creation had not only been detected, it had been measured. The universe was no longer an abstraction. It had become something that could be tested, charted, and understood, a living record written in light. The philosophical consequences rippled outward. For thousands of years, humanity had imagined the heavens as eternal, an unchanging dome where stars lived forever. Now that illusion was gone. The cosmos had a childhood, and if it had a beginning, it must also have a future. The discovery of the cosmic microwave background redefined what it meant to look at the night sky. The stars were no longer ancient guardians of time, but latecomers. Sparks formed from the debris of something far older. Even the darkest corners of space were not empty. They shimmered faintly with the afterlight of creation. Every photon in that glow had been traveling for nearly 14 billion years, untouched and unaltered, carrying within it the memory of when the universe first became visible. This was not just astronomy. It was archaeology on the scale of existence itself. Each measurement of that faint background brought scientists closer to understanding not only where everything came from, but why the universe looks the way it does now. The cosmic echo also challenged deeper ideas about causality, about meaning. What does it mean for something to begin when time itself began with it? If the universe emerged from an initial singularity, what, if anything, existed before it? The discovery didn't answer those questions. It made them more profound. And yet, in its silence, the radiation offered a strange comfort. It spoke of continuity, of persistence, of a universe that remembers. Every human, every star, every atom is woven into that same ancient tapestry, all formed from the cooling embers of the same first fire. By the close of the 20th century, the cosmic microwave background had become one of the most precisely measured phenomena in science. Its temperature, 2.72548 kelvins, was known to 5 significant figures. Its tiny fluctuations, mapped by satellites, revealed the exact geometry of the universe, its age, its composition. It told scientists that ordinary matter made up less than 5% of everything that exists, that the rest is dark matter and dark energy, invisible but dominant. All of this, from a faint hum in the sky. The discovery of the CMB did not just rewrite textbooks. It rewrote humanity's place in the cosmos. For the first time, there was proof, not belief, not myth, but measurable, testable proof that the universe had a beginning, that everything we see, from the faintest particle to the brightest galaxy, arose from a single flash of unimaginable energy. In that moment of realization, the universe ceased to be eternal marble and became living history, not static but dynamic, not permanent but evolving. And so the world of cosmology transformed overnight. An ancient universe became a young one, still expanding, still cooling, still writing its story in the light of its own creation. That faint microwave hiss, once dismissed as noise, had spoken. It told of the moment when light first broke from matter, when darkness learned how to shine. It carried across space and time the memory of when everything began, and for the first time, humanity had heard the echo of creation, and it sounded like noise. In the decades that followed the accidental discovery of a faint hiss in the sky, humanity began to listen more carefully. The static that had once irritated 2 radio engineers was no longer dismissed as noise. It had become the soft hum of eternity. Astronomers now turned their instruments toward that whisper, determined to translate it, to read the first words ever spoken by the universe itself. What they found was not chaos, but perfection, a light so smooth, so mathematically pure, that it could only have come from the universe's beginning. It was not the light of stars, nor of galaxies, nor even of time as we know it, but of an age before matter had shape. To understand it, one had to journey backward, to an era when the cosmos was less a collection of things and more a single blinding ocean of energy. In that early universe, there was no transparency, no stars, no empty sky. It was a furnace without boundaries, electrons and protons colliding endlessly in a plasma so dense that light could not move freely. Every photon was trapped, scattered, absorbed, reborn in an endless dance of energy and matter. For nearly 380,000 years after the Big Bang, this was the only reality, a cosmos glowing from within, but blind to its own light. Then, something extraordinary happened. As the universe expanded, it cooled. Slowly, almost tenderly, the chaos began to settle. Temperatures dropped below 3,000 degrees Kelvin, still hotter than any fire on Earth, but cool enough for electrons to finally bind to protons, forming the first atoms of hydrogen. It was a moment cosmologists now call recombination, though in truth, it was more like creation. For the first time, light was no longer trapped. The universe became transparent, a vast newborn space through which photons could travel freely. Those photons have never stopped moving. They have crossed billions of years and unimaginable distances, stretched by the expansion of space itself. What began as a white-hot blaze has now cooled into a faint microwave glow, chilled to just 2.725 degrees above absolute zero. The fire of creation did not vanish, it merely froze. Scientists began to test this idea. They built instruments sensitive enough to detect radiation not in the visible spectrum, but in microwaves, the long, gentle ripples of ancient light. Every test returned the same answer. This glow was everywhere, bathing the Earth, the Moon, the space between galaxies. No matter where the antennas pointed, the signal remained constant, as if the entire universe was wrapped in a single invisible flame. It was then that physicists realized they were not merely studying radiation. They were studying the fossil light of the universe, an echo that had journeyed unbroken from the moment matter first began to exist. The shape of that echo, its spectrum, became the next great revelation. Using detectors carried by balloons, rockets, and later satellites, scientists measured its intensity across different wavelengths. The result was a curve, smooth, elegant, and perfect, matching precisely the theoretical form of a blackbody spectrum. In physics, a blackbody is an idealized object that absorbs all radiation and emits it with a distribution dependent only on temperature. No natural process, no random chaos could produce such a curve unless it originated from a single unified source. The universe, it seemed, had once been that perfect furnace. The cosmic microwave background was not just ancient light, it was evidence that the entire cosmos had once been in thermal equilibrium, glowing as one immense body before it began to unfold. This perfection astonished scientists. The radiation's temperature was nearly identical in every direction, a uniformity that defied imagination. How could regions of space, separated by distances that light itself could never have crossed since the Big Bang, have ended up so precisely balanced? It was as if the universe had somehow coordinated itself beyond the reach of time. This puzzle would come to be known as the horizon problem, and it hinted at a deeper truth yet to be uncovered. But within that near uniformity, something subtle lingered. Tiny irregularities, faint whispers of difference. When the first sensitive detectors began mapping the microwave sky, they found that the temperature of this ancient light was not exactly the same everywhere. The variations were minute, just tens of microkelvins, differences of a few millionths of a degree. Yet in those faint ripples lay the seeds of everything that would ever exist. In 1992, NASA's COBE satellite revealed the first full-sky map of the cosmic microwave background. It was not flat and featureless as once thought, but gently mottled, a cosmic tapestry woven with faint patterns. Later missions, WMAP and Planck, refined that image with exquisite precision, revealing a map of primordial density fluctuations, the universe's original blueprint. Each small warm or cool spot on that map represented a region slightly denser or thinner than its surroundings in the infant universe. Over billions of years, gravity would amplify those differences, pulling gas into clusters, condensing matter into stars, galaxies, and finally, into the vast cosmic web we see today. What began as a nearly perfect glow became the structure of everything, from spiral galaxies to the atoms in human blood. The pattern was frozen in the light itself, a snapshot of the first moment when the universe had a memory. Scientists began to call it the universe's baby picture, though the phrase feels too simple for what it truly represents. It is more than an image. It is a symphony written in temperature and space, the first measurable trace of cosmic order emerging from primal chaos. The physics of it is precise yet poetic. These variations in the cosmic microwave background are thought to originate from quantum fluctuations, tiny ripples in the fabric of space that were stretched to cosmic scales by the rapid expansion known as inflation. In the first fraction of a second after the Big Bang, the universe is believed to have expanded faster than light itself, smoothing everything while freezing in place these microscopic imperfections. Those imperfections would become the skeleton upon which the universe would grow. It is an idea both humbling and divine, that the vast galaxies now drifting through space began as whispers of quantum uncertainty, etched into the first light of creation. As instruments improved, scientists discovered more within the frozen fire. They began to measure the polarization of the microwave background, the subtle twisting of its light caused by ancient gravitational waves, and the scattering of early photons. These patterns offered a new way to probe the universe's infancy, hinting at the violent birth of space itself. Every detail of this radiation became a question, and every question opened a door to a deeper mystery. Why is the temperature so uniform across such vast distances? What caused the slight asymmetries that led to cosmic structure? And could there be hidden messages within the noise? Evidence of other universes, other inflations, other beginnings. Even as data answered old questions, it stirred new ones. The more perfect the cosmic background seemed, the more improbable its perfection became. To many cosmologists, the frozen fire was not just a relic. It was a paradox, a code written in light, awaiting interpretation. In that soft afterglow, the story of everything was suspended. The universe, once opaque and violent, had cooled into silence, and that silence still speaks. The static of old television screens, the hum between radio stations, the faint whisper picked up by every microwave antenna. All of it carries a trace of this ancient light. It is the most democratic signal in existence, reaching all of Earth, all of time, equally. And though it began as fire, it now drifts as frost, across the vastness of space. The light of creation moves still, stretched, cooled, scattered, but never extinguished. It is the residue of a universe that remembers everything, a whisper frozen in the very fabric of space-time. The frozen fire became the mirror of eternity, showing humanity not what came after, but what came first, and in its reflection, the cosmos seemed to whisper one haunting truth. The future was already written in the cold ashes of the first light. In the quiet aftermath of discovery, a new kind of vision began to awaken. For decades, the cosmic microwave background had whispered its existence across the heavens. A faint, uniform hum, soft as static, ancient as time. But humanity was not content with the whisper. It wanted to see the voice of creation, so it built machines to listen with impossible precision. In 1989, NASA launched the Cosmic Background Explorer, COBE, a satellite unlike any before. Its mission: to measure the sky's ancient radiation in detail so fine that the universe's infancy could be painted, pixel by pixel, in temperature and light. When COBE's first data returned, it did not merely confirm the faint microwave glow, it transformed it. What had once been a formless background became a cosmic portrait, subtle, intricate, alive with pattern. The radiation was not perfectly smooth. It shimmered with faint ripples, delicate variations in temperature and density, imprinted when the universe was only 380,000 years old. To the human eye, the COBE map was almost abstract, a mosaic of blues and reds scattered across the celestial sphere. But to cosmologists, it was revelation. Those tiny fluctuations were the fingerprints of creation, the first disturbances in the primordial plasma that would one day grow into galaxies, stars, and worlds. These were not just fluctuations of heat, they were ripples in the primordial sea, waves of pressure and sound moving through a universe made not of matter, but of plasma and light. In those earliest moments, the cosmos was a vast, luminous ocean of particles and photons so tightly bound that they behaved as one continuous fluid. Gravity pulled matter inward, compressing it. Radiation pushed outward, resisting collapse. The result was a kind of cosmic music, a pattern of acoustic oscillations. Pressure waves that rippled through the infant universe like sound waves across a still ocean. Where the waves peaked, matter was denser. Where they dipped, it was thinner. When recombination occurred and the universe became transparent, those waves froze in place, leaving behind a record of their movement, a frozen symphony written in the sky. It is this rhythm, preserved in the microwave background, that would dictate the shape of everything to come. The spacing of galaxies, the clustering of matter, the very scaffolding of the cosmic web, all were seeded by these ancient vibrations of light and gravity. But as the instruments improved, so too did the clarity of the mystery. When NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, in 2001, it carried sensitivity 1,000 times greater than COBE. What had been a blurry sketch now sharpened into an exquisite image. WMAP's data revealed that the universe was astonishingly flat on large scales. Its geometry balanced between eternal expansion and collapse. It measured the age of the cosmos at 13.8 billion years, confirmed the dominance of dark energy, and showed that only a fraction of existence, a mere 4.9%, was made of ordinary matter. But within that triumph of precision lay something unsettling. When scientists analyzed the WMAP maps, they noticed that one region of the sky appeared unusually cold, a vast patch where the microwave temperature dipped lower than theory predicted. It was not a mere fluctuation. It was enormous, spanning over 1 billion light-years across. They called it the cold spot. Its presence defied explanation. Some proposed that it was simply a statistical fluke, a cosmic coincidence in the random noise of early creation. Others suggested it might be the mark of a supervoid, an immense region of space with far fewer galaxies and less matter, causing photons to lose energy as they passed through. But even that idea could not fully account for its depth and scale. The cold spot became a cosmic wound, a scar in the otherwise perfect fabric of the early universe. When the Planck satellite was launched in 2009 by the European Space Agency, it was humanity's most advanced eye on the ancient light. Planck observed the sky at 9 different frequencies, stripping away interference from stars, dust, and galaxies to reveal the pure, untouched radiation beneath. The data confirmed the cold spot's existence, not an artifact, not a mistake, but a genuine feature of the cosmos. And so, the universe that had once seemed smooth and symmetrical began to show signs of asymmetry, as if some regions carried a different memory, or perhaps a different origin. Speculation grew. Some cosmologists proposed that the cold spot might be the result of something profound, a collision between universes. In certain models of eternal inflation, the universe we inhabit is not unique, but one bubble among countless others, each with its own physical laws and constants. When 2 such bubbles collide, they could leave behind circular imprints, distortions in the cosmic microwave background. If true, the cold spot might not just be a void. It could be the bruise left by another universe, an echo of contact across dimensions. Others looked even deeper, suggesting the asymmetry might arise from quantum scars, remnants of fluctuations that occurred before inflation began. When the universe itself was smaller than an atom, these fluctuations, magnified to cosmic scale, might encode physics we have yet to comprehend, hints of a pre-Big Bang reality, or the fingerprints of higher dimensions curling against our observable sky. In the data, there was both revelation and disquiet. The universe's earliest light seemed to whisper not only of what was born here, but of what might exist beyond. The acoustic peaks measured by Planck, the harmonics of those primordial sound waves, matched the predictions of inflationary cosmology with breathtaking precision. Every note of that ancient symphony lined up with theory, and yet the cold spot lingered, a discordant tone in a near-perfect song. Was it coincidence? Or was the universe trying to tell its story through imperfections? The way a scar reveals history, the way silence gives meaning to sound. The deeper scientists looked, the more fragile the concept of cosmic simplicity became. The background radiation, once thought uniform and eternal, now hinted at complexity. Subtle alignments of temperature variations, an unexpected hemispherical asymmetry, and a faint pattern dubbed the axis of evil, where the largest structures in the microwave sky appeared to align in defiance of random chance. These were not errors in measurement, they were facts, and yet facts without explanation. To some, they were reminders that our cosmos might not be the whole of reality, merely the visible fragment of a greater multiversal ocean, each bubble universe rippling with its own frozen fire. To others, the anomalies were whispers of new physics, clues that the early universe behaved in ways our equations cannot yet describe, shaped by fields or forces beyond the reach of current theory. Each discovery deepened the paradox. The more precisely scientists mapped the cosmic background, the more they realized how imperfectly we understood it. Every new detail revealed both beauty and disquiet, harmony tinged with mystery. The ghostlight of creation, once thought simple and uniform, now appeared haunted by questions that refused to fade. If the cold spot was real, then it carried implications vast enough to redraw the boundaries of existence. It might mean that space itself is not continuous, that our cosmic history began not as a singular explosion, but as a collision, a merging of worlds, a meeting of infinities. Or perhaps it is a mirage, a pattern born of our own limited perception, a reminder that the universe's first light is not only a map of space, but of our struggle to understand it. Either way, the cosmic microwave background had ceased to be a static relic. It had become alive, a living document, rippling with encoded stories of birth, motion, and memory. The primordial sea was no longer silent. Its surface was filled with waves that spoke of deep forces, ancient resonances, and unseen shores. And as scientists traced those ripples further and further back, through plasma, through quantum foam, through the breath of inflation itself, they began to sense something profound, that this ghost light might not only reveal where the universe began, but also how reality remembers. In the frozen sea of creation, humanity found not just its beginning, but a haunting question echoing across time. If there are ripples in our universe, then somewhere beyond our horizon, there may be others still rising. The deeper humanity stared into the faint, ghostly glow that filled the heavens, the more it began to realize that the cosmic microwave background was not just a relic of the past. It was a script, written not in ink, but in light, not in words, but in temperature, polarization, and pattern. A silent code carrying the memory of creation itself. Every faint ripple, every minute asymmetry across the cosmic sky seemed to whisper of forces and moments no longer visible, yet still shaping reality. And so, from these frozen echoes, theory began to rise, fragile, daring, magnificent. The first to emerge was a vision of inflation, a theory so audacious that it redefined the very meaning of beginning. Proposed in the early 1980s by physicist Alan Guth, inflation suggested that, in the first unimaginable fraction of a second after the Big Bang, the universe did not simply expand. It exploded outward faster than the speed of light itself, not through space but of space. In less than 1032 seconds, the cosmos swelled from subatomic size to astronomical immensity, a sudden, exponential blossoming that smoothed away the chaos of creation. Galaxies, stars, and cosmic filaments had not yet formed, but the uniformity seen in the cosmic microwave background, the same temperature, the same glow across billions of light years, could now be explained. Inflation had ironed the fabric of the universe flat. Yet within that cosmic smoothness, there was still texture, tiny irregularities, minute wrinkles in the fire of birth. According to quantum theory, these imperfections were not accidents. They were quantum fluctuations, microscopic tremors in the quantum fields that filled early space. During inflation, these fluctuations, once confined to scales smaller than atoms, were stretched to cosmic size. Each one became a seed, a faint imprint of density, destined to grow under gravity's patient hand into galaxies, stars, and clusters. From the trembling heart of the quantum realm, the architecture of the cosmos was born. It is a thought that borders on the divine, that every galaxy, every world, every being might trace its ancestry to the random flutter of particles in a sea of expanding nothingness. That existence itself began not with order, but with noise, a chaos that inflation transformed into creation. As inflation theory matured, scientists sought its traces in the oldest light. The cosmic microwave background became a testing ground, its subtle patterns a canvas, upon which the universe's earliest behavior had been. Imprinted inflation predicted not only uniformity, but a specific type of polarization in the ancient radiation, tiny twists in the direction of its electromagnetic waves. These patterns, called B modes, would arise from gravitational waves, ripples in space-time produced during inflation's violent expansion. If detected, these B modes would be the smoking gun, a signature of inflation, a direct glimpse into the universe's first trillionth of a second. In 2014, the BICEP 2 experiment at the South Pole announced it had found them. For a moment, the scientific world held its breath, believing that humanity had finally seen the tremor of creation itself. But further analysis revealed the signal was contaminated by cosmic dust, light scattered not by primordial waves, but by particles within our own galaxy. The proof had vanished, yet the hope remained. The search continues through projects like Planck, SPT Pole, and the Simons Observatory, instruments tuned to listen for the faint rustle of gravity waves frozen in the sky. If these signatures are ever found, they would confirm not only inflation, but something deeper, that the structure of the universe is inseparable from the fabric of space-time itself, vibrating like a string before time began. But inflation, while elegant, raised questions of its own. If space could expand so violently once, what prevents it from doing so again? And if inflation can happen once, in one region, might it not occur endlessly in countless others. This idea gave birth to the multiverse, a vast, unobservable ocean of universes, each born from inflation's eternal surge. In this vision, our cosmos is but one bubble among infinite others, each governed by its own laws of physics, its own constants, its own histories. Some bubbles would collapse in moments, others would endure forever. And where two universes collide, they might leave behind circular scars in the cosmic microwave background, faint distortions like ripples overlapping on a cosmic pond. Some scientists studying anomalies like the cold spot have wondered if such a mark might already exist, the bruise of another reality pressed against our own. But the multiverse, though seductive, treads a delicate boundary between science and philosophy. It is a theory that may never be proven, and yet its logic grows naturally from inflation's mathematics. If inflation is true, eternal inflation may be inevitable. Beyond inflation, other possibilities shimmer at the edge of understanding. Some cosmologists have revived the idea of a cyclic universe, one that expands and contracts endlessly, each Big Bang followed by a big crunch, then reborn again. In these models, the cosmic microwave background might carry faint echoes of previous universes, remnants of cycles that existed before ours, their information woven into the patterns of temperature and polarization we see today. Others imagine topological defects in space-time, cosmic strings, domain walls, and textures left behind as the universe cooled, like cracks forming as ice solidifies. If they exist, they could distort the microwave background, producing small but measurable irregularities, tears in the fabric of early reality. So far, no clear evidence has emerged, but the search continues. And yet, the most haunting possibility lies not in alternate universes or exotic relics, but in what the cosmic light itself might remember. The CMB is not just radiation, it is information. Encoded in its fluctuations is a complete record of the universe's infancy, its density, geometry, and even the fingerprints of the fundamental forces themselves. Physicists suspect that by decoding this cosmic pattern, we might uncover physics beyond the standard model, clues to energies and dimensions unreachable by any particle collider. If inflation was real, it operated at energies near the Planck scale, where gravity and quantum mechanics intertwine. In that regime, the known laws of nature dissolve, and new ones, perhaps involving superstrings, extra dimensions, or quantum gravity, must emerge. The ancient light may carry their echoes. Every photon of the cosmic background has journeyed across the expanding universe for nearly 13.8 billion years, untouched, unaltered, unforgotten. Each one has been stretched by time, but not erased, its wavelength now 1,000 times longer than visible light, yet still carrying the vibration of its origin. Some cosmologists even speculate that the CMB might hold subtle imprints of entanglement from before the universe's separation into space and time, patterns of correlation that defy classical explanation, hints of a pre-space-time order. If such traces exist, they would mean that the universe remembers not only its birth, but the physics of a realm that existed before birth, a reality beyond space, beyond causality, beyond what words like before can even describe. From these speculations arises a new kind of awe, not the awe of ignorance, but of limit, that the universe has given us clues precise enough to glimpse its origin, yet not complete enough to explain it, that in the soft hum of microwaves, we may be hearing both the first breath of time and the silence that preceded it. To gaze upon the cosmic microwave, background is to see the edge of what physics can touch, and to sense the infinite that lies just beyond. In those ripples of light, humanity sees not only the trace of the Big Bang, but the fingerprints of possibility, inflation, multiverse, cyclic rebirth, quantum scars, and gravitational whispers. Each theory reaches toward the same luminous horizon, trying to answer one impossible question. How does something emerge from nothing? Perhaps the ghost light holds the answer, still encoded in its faint polarization, still whispering across space. Perhaps one day, when instruments grow sensitive enough, it will tell us what existed before existence itself. For now, it remains the most ancient of mysteries, a message written in radiation, the handwriting of creation etched into the sky. And though scientists read its symbols in equations and maps, There is something deeply human in the silence it carries. A reminder that to understand the cosmos is not only to measure it, but to listen. Because in the end, this light, older than galaxies, older than matter, is still speaking. And its language is the language of beginnings. In the frozen stillness of Antarctica, beneath a sky so clear it seems carved from glass, a machine waits. Its gaze is fixed not on stars, but on the invisible hum that fills the cosmos. A whisper older than the first atoms. This is the South Pole Telescope, a cathedral of metal and mathematics, standing in the silence of ice. Its purpose is not to see, but to listen. Every night, it turns its ear toward the void, capturing the faint, uneven breath of the universe itself. Elsewhere, high in the Chilean Andes, another sentinel listens, the Atacama Cosmology Telescope. It rises from the desert like a relic from a forgotten faith, surrounded by air so thin it remembers almost nothing of the world below. Together, these instruments form a network of cosmic archaeologists, charting not the ruins of stone, but the ruins of light. They are the machines that listen to creation. The faint microwave glow they chase, the cosmic microwave background, or CMB, is the oldest message ever sent. A transmission not from a distant civilization, but from the universe itself. Each telescope measures it with impossible precision, tracing the smallest ripples in its temperature, the subtlest twists in its polarization, the tiniest distortions in its path through the gravity of galaxies. These are not just fluctuations in energy, they are echoes of forces that shaped everything that followed. Gravity, matter, and the first light that dared to escape the cosmic fog. The Planck satellite, launched by the European Space Agency in 2009, brought this listening to its most exquisite form. It drifted in the cold shadow of the Earth-Sun L2 point, 1.5 million kilometers away, where light and shadow balanced perfectly. For nearly 5 years, it listened without rest, scanning the entire sky again and again, mapping the universe's faintest afterglow to the precision of millionths of a degree. The result was a portrait of unimaginable detail, a glowing oval of mottled color, the blueprint of everything that exists. Every pixel of that map is a moment from 13.8 billion years ago. It shows where matter gathered, where emptiness expanded, where gravity first sculpted the cosmos. The Planck data confirmed what earlier missions like COBE and WMAP had hinted, that the universe is astonishingly flat, uniform, and yet delicately laced with imperfections, the seeds from which all structure was born. It revealed the universe's age, its composition, and even the invisible tug of dark matter and dark energy woven into its frame. But Planck's map also deepened the mystery. Hidden within its perfection were anomalies, faint asymmetries, temperature cold spots, alignments that defied the expected randomness. Were these artifacts of observation, or signatures of something deeper, something written into the geometry of space itself? To answer that, humanity built more ears. The South Pole Telescope and Atacama Cosmology Telescope began to refine Planck's vision. They traced the polarization of the CMB, the way its light was subtly twisted as it scattered off electrons or bent around massive galaxies. These polarization patterns became a new kind of code. Within them lay the potential fingerprint of gravitational waves, ripples in space-time itself, born in the first instant of creation. If detected, such waves would confirm the most audacious idea in modern cosmology, that in its first breath, the universe expanded faster than light in an instant of furious inflation. Space itself ballooned from quantum size to cosmic scale, stretching microscopic fluctuations into the vast ripples that became the scaffolding of galaxies. Inflation was not just an explosion, it was the transformation of the impossible into reality. Detecting these primordial gravitational waves would be like hearing the sound of that moment, the universe's first vibration, its first note in the cosmic symphony. And so, in the Antarctic night, the BICEP telescope, a small, unassuming array of detectors, was built to listen for those waves. In 2014, BICEP 2 announced what seemed like the first whisper of that ancient sound. A curl in the polarization pattern of the CMB, known as a B-mode signal. It was heralded as the possible detection of gravitational waves from inflation, a glimpse of the universe's birth cry. But the joy was brief. Further analysis revealed that the signal was not entirely cosmic. Interstellar dust, glowing faintly within our own galaxy, had mimicked the ancient pattern. The sound had been an echo, not a voice, yet the pursuit did not end. It only became more devout. The next generation of instruments like Bicep 3, the Keck Array, and the upcoming Lightbird mission from Japan continue the search. They refine their sensors, cool their detectors to near absolute zero, and listen to the silence between the galaxies, waiting for the faintest tremor in the fabric of space-time. Each machine, in its own way, is an act of faith, a belief that buried in the cosmic noise lies the first word ever spoken by the universe. And while some instruments listen to the microwave afterglow, others look ahead to the galaxies it birthed. The James Webb Space Telescope, orbiting in the same shadowed haven where Planck once floated, peers deep into the cosmic dawn. Its golden mirrors catch the faint light of the first stars, the earliest galaxies igniting in a sea of darkness. What Webb sees are the grown descendants of the primordial ripples frozen in the CMB, the structures those ancient sound waves foretold. The connection is profound. The cold static mapped by Planck is the score. The galaxies Webb sees are the music now playing. Between them lies the entire history of the universe, from silence to sound, from chaos to structure, from fire to life. Scientists trace this continuum with astonishing precision. They measure how the gravitational pull of galaxy clusters bends the CMB's light, a phenomenon called lensing, revealing both the shape of the universe and the invisible scaffolding of dark matter. They map how the expansion of space stretches the patterns of temperature, how polarization angles twist under cosmic shear, how quantum fluctuations frozen in the first instant may still echo through the vacuum today. In these measurements, the universe becomes less like an object and more like a memory, a pattern of vibrations still unfolding. From the high plateaus of Chile to the frozen poles of Earth, from orbiting satellites to future missions waiting on the launch pad, every instrument adds its thread to this tapestry of listening. And though each experiment refines the picture, the hum remains, soft, omnipresent, eternal. There is something profoundly human in this act of listening. To build machines capable of hearing what no ear can hear, to decode whispers that have crossed the entire age of existence, to look for meaning in the residue of silence, it is an act of wonder as much as of science. For what these machines capture is not just radiation. It is time stretched thin by expansion, cooled by eternity, and delivered into the hands of beings who can finally understand it. The universe, it seems, has not stopped speaking. We have only just learned how to listen. And in the faint hum that surrounds us, in the static that fills the gaps between galaxies, there lingers a truth that no instrument can yet measure, that creation itself was not a moment, but an echo still unfolding, waiting to be heard. If the universe has a voice, it speaks not in words, nor in light, but in the quiet harmony of its own memory. Across the vast black canvas of the universe, there remains a light that refuses to die. It does not shine like a star, nor blaze like a quasar. It glows with the patience of eternity. A faint, unbroken murmur that seeps through every corner of space. It is older than any atom, older than the galaxies that now drift through its glow. It is the universe remembering itself. This is the afterglow of creation, the cosmic microwave background, still rippling softly through the vacuum, still echoing the first fire that once filled all of existence. It has watched everything change, and yet it has never changed itself. Every star that has burned, every planet that has cooled, every life that has arisen beneath its invisible tide, all have unfolded beneath this ancient radiance. It has been the silent witness to everything that has ever been. There is something haunting in that endurance. 13 billion years have passed since this light was freed, since the universe exhaled its first clear breath and let photons travel freely through space. In that time, everything solid has changed. Stars have been born and died. Galaxies have collided and scattered, and the very fabric of space-time has stretched like cooling glass. Yet the afterglow remains, stretched, dimmed, cooled to near nothingness, but still there. It is now only a whisper, its wavelength a few millimeters long, its temperature barely above absolute zero, 2.725 Kelvin. But in that whisper lies the memory of a cosmos in its infancy, when temperatures soared above 3,000 degrees and the universe burned with a brightness no eye could endure. The cosmic microwave background is not merely radiation, it is time made visible, a fossil of light, the first signal ever released into the emptiness. And somehow, across eternity, it still speaks. When humanity first stumbled upon it, by accident, through the static of an antenna, it was as if the universe itself had cleared its throat after billions of years of silence. Since then, we have learned to listen more closely, to strip away the interference of our own world, to isolate the hum beneath the stars. And what we found there was not chaos, but order, not emptiness, but structure. Within that faint and ancient glow lie the fingerprints of everything to come. The tiny fluctuations in its temperature, mere millionths of a degree, would one day become galaxies, clusters, and the filaments of cosmic web that stretch across the sky. The cold and the hot, the dense and the rare, these were the first inequalities, the first seeds of creation's asymmetry. Without them, there would be no stars, no planets, no eyes to see them. In its silence, the cosmic microwave background tells the oldest story, how simplicity gave birth to complexity, how uniform fire cooled into matter, and how the fabric of space began to fold itself into patterns of infinite beauty. And yet, it tells another story too, one about endurance and memory, because this light has outlived everything that first cast it. The plasma that once glowed with its brilliance has long since vanished. The atoms it once illuminated have been scattered and reformed into dust, into stars, into life. But the light remains, unchanged except by time's long stretch. It has crossed the abyss while everything else has burned and faded. It means that the universe remembers. Every photon that drifts across space today carries with it a piece of that beginning, a silent record of the first moment the universe became transparent. Those photons have touched nothing, spoken to no matter, for billions of years. They travel still, straight and tireless, carrying the echo of the first dawn toward the endless dark. And within that realization lies a quiet paradox, that we too are part of that same memory. The atoms in every living thing were forged in stars that themselves were born from the density ripples frozen in that ancient glow. The carbon in our cells, the iron in our blood, the calcium in our bones, all trace their ancestry to the tiny imperfections imprinted in the CMB. In that sense, we are not separate from the afterglow. We are its continuation, fragments of light turned into thought. It is as if the universe, through the long evolution of stars and matter, has built a way to look back at its own birth, to see itself, and wonder. Humanity has become the consciousness of this ancient light. The same photons that once illuminated the newborn cosmos now illuminate our understanding. Through machines that orbit above the Earth, through antennas buried in ice, through equations written in the language of physics, we have translated a whisper into a story that begins with a flash so immense it transcends imagination, and ends, for now, in the quiet reflection of minds capable of listening. In the vastness of space, that is no small miracle. Because the light that speaks to us today began its journey long before there were eyes to see, or words to describe, or time to measure. It has survived the expansion of all things, the cooling of eternity, the rise and fall of galaxies. It drifts now through an ocean of silence, a sea without shore, where the temperature of reality itself is almost still. And yet it endures, unbroken, undiminished. Somewhere in that endurance lies an unspoken truth about existence, that even in decay, there is remembrance. Even in cooling, there is persistence. Even in silence, there is sound waiting to be heard. Cosmologists sometimes call it the afterglow of the Big Bang, but perhaps that name is too small. It is not only an afterglow, it is a pulse, a residual heartbeat that has never ceased. It is the universe's first word, still echoing softly across everything that came after. In its faint glow, we see the outline of our own impermanence. Every human life, every civilization, every dream and idea has unfolded beneath that unblinking light, and yet it will continue long after we are gone. Long after the last star has burned out, when even black holes have evaporated, the photons of the CMB will still drift, cold and ancient, through a universe that no longer remembers warmth. It will be the last visible trace of what once was, the final ember of a fire that began everything. And so, when humanity turns its instruments toward that whisper, It is not merely searching for data or confirmation. It is listening for meaning. The cosmic microwave background is not just an echo of physics. It is a mirror of our own longing to understand, a reminder that we too are made of the same light, bound by the same laws, carried forward by the same expansion. The ghost light of the universe has outlived stars, outlived galaxies, outlived time as we perceive it. But through us, it speaks again, transformed into knowledge, into poetry, into awe. We are its continuation, brief, flickering, conscious moments of the same light that once filled all things. And in that realization lies something beautiful and terrifying. That creation never truly ended. The act of being, of unfolding, continues still. Not as a burst of flame, but as a whisper that flows through everything, every thought, every breath. Every photon that brushes past the edge of the cosmos carries that same truth. In the silence between stars, it hums softly, endlessly, patiently, the sound of a universe still remembering how to exist. Every photon that drifts through the dark once burned at the heart of everything. To look upon it is to look back through eternity and to realize that creation never stopped. It only learned to whisper,